We are ocean scientists for Informed Policy, and we want to bring the latest ocean science to policy-making audiences.
Hi, my name is Natalya Gallo, and I'm a PhD student at the Scripps Institution of Oceanography. Today I want to talk to you about ocean deoxygenation, which is the loss of oxygen from the ocean due to climate change. This creates an issue of oxygen supply and demand.
Oxygen is necessary to support life on Earth. In water, oxygen is found in a dissolved form and is harder to extract than in air. Two key processes supply the ocean with oxygen. Like plants, algae in the ocean use the sun's energy to photosynthesize and produce oxygen. In fact, half of the oxygen in the air we breathe is produced by microscopic phytoplankton in the ocean, making the ocean an important lung of the planet. Oxygen also enters the ocean from the air through mixing at the surface. As surface waters become warmer with climate change, they become more stratified, thus reducing how much oxygen is getting mixed into the water. Warmer water also holds less oxygen, so as ocean temperatures warm around the world, the ocean loses its ability to hold as much oxygen. Long-term ocean monitoring shows that as carbon dioxide levels in the atmosphere rise and global temperatures warm, the supply of oxygen in the ocean declines. So what is the demand for oxygen in the ocean? Almost every organism in the ocean uses oxygen to produce energy essential for cellular processes. For this reason, oxygen plays a key role in structuring marine ecosystems. Warmer ocean temperatures don't just decrease the supply of oxygen in the ocean, they also increase oxygen demand in marine bacteria and marine organisms. Climate change is causing an oxygen supply and demand imbalance in the ocean, both decreasing oxygen supply and increasing biological oxygen demand. The Intergovernmental Panel on Climate Change predicts that oxygen levels in the ocean will continue to decline in the 21st century. Oxygen loss in the ocean is bad news for aerobically active animals like tuna and marlin, which are important fishery species. Some organisms, such as jellyfish and some squid, are tolerant of low oxygen conditions, but fish and crustaceans require higher oxygen levels and are highly vulnerable to oxygen declines.
Low oxygen areas called oxygen minimum zones are already present in the Pacific, Atlantic, and Indian Ocean, and these areas are expanding horizontally and vertically with climate change. These changes are happening at both local and regional scales around the world.
Oxygen minimum zone expansion is evident in all tropical ocean basins and throughout the subarctic Pacific. In the tropical Atlantic, this has resulted in a 15% reduction of vertical habitat for blue marlin and tuna in the last 50 years. Off California, subsurface waters have lost 20 to 30% of their oxygen in the last 25 years, leading to more hypoxia exposure for rockfish in the Cowcod Conservation Area. While fish and crustacean die-offs are one extreme impact of oxygen loss, marine organisms can also experience other negative impacts, including effects on behavior, reproduction, and growth. These individual-level impacts can have large ecosystem-level consequences.
So how do we know that oxygen levels are changing? We know because in some areas, good measurements are available that document these changes.
As scientists, we collect data on dissolved oxygen in the ocean using ship-based measurements with CTDs and bottle samples, and using oxygen sensors attached to moorings, autonomous landers, and autonomous profilers called Argo floats that survey the world's oceans. Some areas in the ocean are well studied, but others are not. Right now, there are almost 4,000 Argo floats profiling the world's oceans, but less than 10% of them collect data on oxygen, leaving many areas in the world's oceans understudied. If we don't measure oxygen levels, then we don't know how they're changing with climate change. We need better monitoring of local and regional changes in oxygen levels and the ecosystem effects. The potential consequences of ocean oxygen loss are profound, but deoxygenation does not act alone. Together, warming, acidification, and deoxygenation present a triple climate change threat for marine life. Marine ecosystems provide us with essential ecosystem services, and changes to these ecosystems leave coastal economies vulnerable. For this reason, policymakers should consider this important but under-acknowledged climate change impact. Do you know the oxygen supply and demand in your local marine ecosystems?
We are ocean scientists for Informed Policy, and we want to bring the latest ocean science to policy-making audiences.